Welcome to From the Experts, a new podcast that is bringing the best in the business to talk about some of the issues that contractors, designers, and others in the building industry run into. And one of the areas that I keep hearing about is envelope and enclosure. So we're going to start with Tony Ferrante, who's joining us to talk about building enclosure errors. Tony, welcome to the podcast.
Thanks for having me here. I'm excited about doing this.
So I'm going to start a little bit with Tony's background. So again, he's today's expert. So he's an RRO, CSI, and CDT. I know him through CSI, where I saw an incredible speech he gave on the very thing we're going to go through today. So he's a senior building enclosure consultant for BPL Enclosure. He'll talk about them in just a sec. He's been at this a long time, 40 years. I'll bet he doesn't admit that often. Started in ready-mix concrete and then has been through roofing and a bunch of other parts of the industry to really understand enclosure from a 360-degree perspective. He's been a manufacturer's rep as well, so he's really looked at this from the ingredients as well as the deliverable. Tony, before we go on, let's talk a little bit about what BPL Enclosure is.
Okay. So BPL Enclosures is a national team of building science experts. I don't like to tell people that I am the expert. I am a knowledge broker. I facilitate knowledge through my team. And we have every facet of the building enclosure encompassed with pure D experts on the different fundamentals that make up everything that is the six-sided box for the enclosure. We offer third-party peer reviews for designers. We offer QA work for contractors and owners. And sometimes we act as the prime designers and architects of record for rehab and renovation projects.
Love it. So you do this for a living.
Yes, sir. Very much so.
So let's talk about why people even use an enclosure consultant.
Well, because the mitigating the risks of being a designer or a constructor is the pure fact is that 70% of all lawsuits are from water damage. So if you think about how much risk there is in building a building and maybe getting sued if you get water intrusion into that building, over 90% of the failures of that building come from just 1%, which is the enclosure.
And in another venue in my other podcast, I'd spoken with a company that gets pulled in 6 months or a year after a building is up to remediate issues. And they said the same thing from the other angle, that like most of the times people bring them in is to fix things that are about the enclosure. Before we move on, I want to make sure we cover one thing, and that is, people use the word envelope a lot, and you use the word enclosure, and I understand them to mean the same thing, but talk about that a little bit, why we're using one versus the other.
Well, the terms in envelope and enclosure are interchangeable with one another. Many years ago, when the Roof Consultants Institute changed from that name to encompass building enclosure consultants as well, there was a massive dialogue in trying to decide whether they would be the International Institute of Building Envelope Consultants or Enclosure Consultants. And it was decided that the term envelope leaves too much at risk because an envelope does not actually separate, whereas the word enclosure more closely encompasses the fact that you're trying to separate the interior space from the exterior space by enclosing it, whereas an envelope could still have air leaks, vapor leaks, thermal leaks, and such. So IBEC is the International Institute of Building Enclosure Consultants. And with the International Building Code going more towards the word enclosure, enclosure is just much more, the industry is moving toward being able to use that versus the word envelope.
Love it. So for those listening, it's the same thing. We're
Yeah.
certainly what we're talking about would be what you mean by envelope. It's just a better word as we, move forward. Awesome. So let's start with what is the building enclosure? I think so. Before we go too deep into this, we're going to cover these ideas almost in chapters. So you're going to see us kind of do one thing, then another, so that later on you can go back and if you miss something or you want to hear something again, it'd be easier to find. So we're going to start
Yes.
with that.
Well, the building enclosure, in its most simple term, is the enclosure that separates the interior space from the exterior space. And when that gets to be something that you have to pay closer attention to, is it's not, oftentimes it's not exactly what you might think it is. Whereas in this graphic, you can see that this attic space, the line of the envelope of the building is the roof all the way and the wall all the way up to the top. But the enclosure actually has a line that comes down because the air barrier, the thermal barrier misses that part of that attic. So it's not the exterior of the building, it's the delineation point between the interior conditioned space and the exterior natural space. We call it a
And
six-sided box.
yeah. And, obviously some of that is not always obvious on the drawing, or do you usually find that it's, I mean, there's a whole method of identifying where your barriers are versus where they aren't, right?
Absolutely. That is why in our third party peer reviews and our design reviews, we actually delineate what are the thermal barriers, what are the vapor barriers. And the air barrier is the most important one that gets looked at on the third party peer review because it has to be continuous. And an older architect told me that when he was being trained, he would use his pencil and he would draw his air barrier. And his mentor taught him that if he ever lifts that pencil off the paper, it's no longer an air barrier because it's not continuous.
And do you find, again, like some of this sounds obvious, but people think that they have a barrier and they don't, and you're actually telling them, well, it isn't where you think it is. This is actually where everything is stopped, and you've got things exposed that you didn't think you had exposed.
Absolutely. That happens so often because with all of the different trades that are involved and the different things that are part of the enclosure, it may be continuous until that trade stops. And then when it picks up with the next trade or the next building material and starts, it's always going to be the marriage of the two lines that always seems to be the problem. The devil's always in the details, and marrying systems and barriers is the tricky part of it. And that's why you have to take a look at it.
I think some of what we're going to cover today is the sort of thing that a QA team or a GC is going to be looking for, right? Areas where one trade or another might have, done something that sub-optimizes, shall we say, the barriers.
Exactly.
For example,
For example, if your window is improperly flashed and moisture gets in there and has no way to get out, it's going to eat up the surroundings and it's going to cause horrible problems. You can see the deterioration of the materials. You can see the darkness, which very often means mold. And that's because the enclosure was not true.
and this is one of those times in construction where, it isn't always obvious right now, right? What's happening or what could cause an issue. It seems like a lot of what makes enclosure consulting and a well-done enclosure work is that there's no space, there's no little gaps that over the course of 6 months and 15 rains can cause a lot of issue, right? Is it you're talking about accumulation from small gaps or small holes? I mean, obviously sometimes there's a big gap and rain gets in, but it seems like a lot of the times like this would probably be an example, right? Where what seemed like it was good enough, just a little gap or a little area was enough for the moisture to get in there and stay there.
Correct. There's some further we'll talk about a little further, but when you get those problems, they may not manifest themselves for years,
Yeah.
sometimes a decade, 10 or 15 years after the construction has happened. And you don't even realize what's happening because, if you think of moisture damage as a cancer, you can have cancer happening for years before you get any symptoms. You can have water damage that's occurring for many, many years before you ever get any symptoms that you have a problem. And then once you open it up, it's like, oh my Lord, what do we do now?
That makes sense. We've got another one.
This is a storefront window. It's the same situation where the water has gotten behind there. That probably showed itself a whole lot faster than that last one because the water was coming into the location. But it was it was not flashed correctly. And instead of the water being able to drain to the outside or dry through design drying, it just came into the building. And so, once again, it was something that was a design issue or the constructability of it. We'll go into more about some of the pitfalls with normal construction that you will find.
Oh, I think we got one more.
We got one more about if you get it wrong, bad things happen. This is deficient roof ventilation. You're not getting the proper air circulation. You've got overheating, you've got rippling, you've got problems where your shingles have separated from the substrate, and this can cause air and moisture infiltration underneath the shingles, and it can cause the expected life of the roof to diminish quite substantially in its performance.
Yeah. So, and because this is going to be viewed on video, what you're seeing is a roof with the ripples that Tony was talking about, where, it's deteriorated because, again, they didn't. Well, so now we're going to go into kind of the chaptery things. And let's talk a little bit about rainwater management. You've got these 4Ds, right?
Right. When you get into the actual building sciences, it's much easier to approach your enclosure if you think about just the actual science of the physics of building sciences. So the first way to manage your rainwater, the easiest way, the first D is deflection. If you have a design where the water comes off and in dripping down to the ground through gravity, it doesn't run down the face of the building, you're establishing a great parameter where you're not going to get the water to come back into the building. Things that don't get wet don't leak.
Right.
So that's why on copings and drip edges, they all have the little kick out so that the water coming down kicks away from the building and can go to the ground unimpeded versus just running down the side of the building, carrying dirt with it and possibly entering back into the building.
And so these 4Ds become basically a checklist, right? As you're saying, as rain or other precipitation comes, are we doing at least one of these four? Is that right?
Absolutely. Absolutely. So the next one is the drainage. Masonry, there's a graphic here for a masonry wall. Most people are familiar with weeps. What happens oftentimes in the construction of it, the building, is someone who's not familiar with the function of drainage thinks the weeps are a problem, and you will find the lower skilled tradesmen caulk over the weeps or put masonry over the weeps because they don't understand the need for it to drain.
And weeps are water coming, primarily actual like liquid coming out. Is that right? Is that how you think about it?
That is correct. That is to allow liquid water to run back out from generally the wall, but also curtain walls, storefronts, windows. They have weeps as well.
So key takeaway, don't block weeps.
Because I can tell you that there have been hundreds of instances where we have done forensic leak studies because we've been called in after the fact to find out why there's water damage or water intrusion into the building. And we very, very often find that the weeps have been blocked. Because as I said, there may have been one leak and someone went out there to say, oh, let's fix the leak. So they grabbed a tube of sealant and started going around sealing things up, and they block the weeps. And what started off as a little problem becomes a massive problem because it's not doing what it's designed to do. The second D, if you're blocking off the drainage, your enclosure is not going to work.
It feels like this is the kind of thing that might happen later in a project, right? So like everything's up, we've moved on, but then at the end, somebody's gone through and like another sub has gone through and done something. And for the contractor that's, responsible for checking to make sure this doesn't happen, this feels like very often you're going to want to keep an eye on this at the end of a project as opposed to the middle. Is that right?
Very, very good. Yes, especially oftentimes multifamily dwellings, big commercial buildings, everything will get put up, and then the final thing is the fit and finish. And they'll have all of the punch windows will still have all the stickers and everything on them, or paint, overspray, and they get crews to come in and they razor blade the windows and they clean the windows and stuff. And then somebody gets tasked to fix anywhere where there's missing sealant. And the guy who's maybe the newest guy out there or an apprentice is told, go fix any openings. And he goes around and he sees these little openings and he takes his gun and he fixes it. And he doesn't have any understanding of the fact that because he hasn't been properly trained that he's not supposed to be covering the weeps.
Got it. And just to finally that point is the water may have gotten in there 100 different ways, right? Some of it could have been dew, some of it could have been actual water flowing in, it could have been, temperature changes and all sorts of things, right?
Right. Well, because today's curtain wall systems are set up so that water is part of the design to get in. And the problem is if it's designed to get in, some of the external sheathings, some metal wall panels, for instance, when you put up a metal wall panel system, it's going to stop about 80% of the precipitation. But by design, it's not a watertight, airtight system of cladding. So if the cladding allows water to get behind it, then you've got your water resistant barrier behind it that can then funnel it down and it can get out through its weeps and its drainage cavities. And if those get blocked off, then you've shot yourself in the foot.
Yeah. Now you've got a little water tank that's going to do all the fun things standing water does.
Yes, exactly.
Well, so the other side of that is drying.
Correct. Drying, more and more designs are starting to understand that if in that cavity wall system, if they also provide an airflow through comb vents at the top of the wall, then they're creating a convection flow of air in that cavity. And they're actually helping facilitate regulating the drying of the moisture that gets in there. And it's just a much better building practice if you think of the drying for this. And also there's drying when a cavity wall operates opposite from how it's designed and the moisture gets in, but there's no way for it to dry, then it sits in a static position. And the only thing for it to do is deteriorate its surroundings or try to intrude into the actual living space of the enclosure. There's a really good example of that coming up on water that's gotten in but had no way to dry. And so all it did was do really bad things to the building.
Cool.
Then the fourth D is the durability. And the fourth D is kind of fudging it a little bit because deflection, drainage, and drying all contribute to the durability. But the key thing to think about with durability is that you have to build the building in layers so that the durability doesn't suffer because you've put something that's of lower durability inboard of something that has greater durability. A great example is a brick masonry wall that you expect those bricks to last for 40 years, but you've taken a VE for lower price point brick ties that only have a 5 to 10 year life before they corrode out and need to be replaced. And all of a sudden you're having to tear out a 40-year lifespan brick to get to a 10-year brick tie.
Hmm.
And so you have to pay attention to that because it can cause serious issues when your durability flip-flops in its projected lifespan.
Makes a lot of sense.
Well, this dovetails well into what I just said. This is a perfect example of a wall that's operating as it should have been, but it wasn't designed to allow for drying. If you look at the first part, you've got a water resistive barrier behind this stucco, and it was doing its job. It was water resistive, not watertight, and the water was getting behind the stucco. But once it got in there, there was no way for it to drain or dry, so the water just stayed behind there. And what I was saying about the fact that they don't often show themselves through symptoms until later on, this building owner had no idea he had issues with his wall until after a number of years, people started complaining about odors. And when they first opened up the stucco, they saw the water resistant barrier and they said, well, it looks good out here. It can't be this problem. And we went beyond that. And in cutting the water resistant barrier, the OSB that was behind that, if you can picture the consistency of a bowl of shredded wheat with milk, the dry mulch that's out around your trees
Yeah.
sometimes. and it was just impregnated with mold and organic growth, and the wood studs were deteriorating. This was a massive problem simply because there was no allowances for drainage and drying.
Love it. Well, they didn't love it.
No, drainage and drying are essential.
So our next, now that we've talked about getting water in and out, let's talk about air leakage.
So air leakage control, it's a pretty simple starts. The slide starts off with what's the element, and it's your air barrier. And as I said earlier, your air barrier has to be continuous. If you're looking at a set of drawings and you're tracing the air barrier, if you lift your pencil up, your air barrier no longer works because your six-sided box has got to be able to keep the air. And oftentimes when I'm doing this in my presentations, and I've done them all across the country, someone will invariably come up with the fact that the old misnomer, well, buildings have to breathe. And that's a fallacy. Buildings don't breathe, humans and animals breathe. And when we breathe through defined orifices so that it can be conditioned. Buildings need to be thought of in the same way. We don't breathe through our skin. We breathe through where we're supposed to breathe. The
Hmm.
building should only, quote, breathe through ventilation so that it can be conditioned and it can be regulated.
That makes a lot of sense. And kind of what we're talking about is when it doesn't, you have the issues we're about to see.
Exactly. So the slide says, where does air leak? The Cliff Notes version of it is everywhere.
Yeah, yeah.
Air comes in everywhere in your building. You've got opportunities for there to be air leakage. The devil is in the details. Every single detail is a possibility for air to intrude and move in places you don't want it to do.
This speaks to what we talked about in the beginning, right? Where structural penetrations are often where things happen later, where a trade has needed to put in something, and in so doing, they've punctured the air barrier. And maybe they didn't know to, or maybe they didn't adequately, or maybe they thought someone else was going to seal it back up, right? So that's one of those details that seems like it sneaks in is as you're, especially when you're trade stacking and, there isn't enough time and all the 100 other reasons why people do the best they can in the time they've got, but issues happen.
I find that quite often in rehabilitations and adaptive reuses where the building was built in the 50s and it got turned into office space in the 2000s, and now they're wanting to turn it into residential and retail. And during the course of that time, they started off where they had television sets that were on antennas, and then they decided to go with cables. And then they decide they're going to put in some sort of satellite communication. And each trade that comes out to run this new wiring punches holes, fills it to what they think is an acceptable norm for them at that time,
Yeah.
and then they move on, and you've got a break in your air barrier continuity.
Yeah. And they're not necessarily trained on enclosure at all, right? Their job is to make sure the signal gets in and, the wire doesn't break.
Absolutely. So air leakage, its biggest problem is the amount of moisture issues that come with air leakage. You want to go to the next one because of the dew point. So when that air leaks, it carries a substantial amount of moisture with it, and it can cause condensation. The example is always the glass of Coca-Cola with the sweat on the outside of it or on the inside of your window panes. But where it really becomes a problem is when you can't even see the condensation because it's happening inside of your walls.
Yeah.
So you have to control your vapor diffusion, and vapor diffusion is a process where the saturation pressure and the vapor pressure and your temperature have to have lines to show where the temperature is going to drop based on its passage through whatever thermal barriers you've got on your building. And when you've got problems where your saturation pressure and your air pressure meet inside of the wall, you can end up with condensation occurring inside the wall. And that's what you want to prevent from ever happening. And you can't prevent vapor pressure because it is going to move from the area of least or sorry, it's going to move from the area of the highest concentration to the area of the lowest concentration. The example of the food dye, you've got a huge ball of food dye, and it is just through natural occurrences, it's going to move to the area where it is equally diffused. Nature abhors a vacuum. That vapor is going to move. It has nothing to do with whether it's being moved or heated or pushed. It's going to diffuse.
Well, this speaks to, some of the surprising results, right? Is that there isn't any air movement and yet it's diffusing. That's kind of counterintuitive, but you just showed it with, and well, anyway, you illustrated it with the food dye, and also the fact that it'll diffuse through permeable materials, which is most materials, to be honest. So the idea being that if there's air coming through, it's going to find a way to get where you don't want it to be. The moisture
That's
is
right.
going to find a way to get
The,
where you don't want it to be.
and so that's why vapor, it's sometimes always called vapor barriers, but it's really more of a vapor retarder. And there are different classes of vapor retarders. But before you start worrying about that, you pay attention to the condensation. And the condensation, the hard way to figure it out is using a psychrometric chart,
Yeah.
where you figure out the temperature and how much humidity it can have and how much moisture is in that air and at what temperature is it going to cause a problem. But the easiest way today is there are many, many online dew point calculators that can tell you if you've got the temperature and the relative humidity, it'll give you the dew point. And you plug in the different things that you need, and it will help you figure out where your dew point's going to occur based on what the conditions are at that time in that location.
And I would assume, though, for most buildings that are in a place where people would be, dew is going to happen, right? So
It you're
when do you do this? When do you kind of try to model out the dew points and all that? When does that help you?
it is always something that should be cognizant in the design of a building because your dew point is going to impact the building based on where it is, what it is doing. You may have a cookie cutter building set of plans that we're going to build this tire care shop using this set of plans, and you're going to have a much different reaction to where your thermal barriers and things need to be if you're going to build that prototype of that tire shop in Alaska versus if you're going to build it in Florida. Because your exterior conditions, your interior conditions generally stay the same on what's comfortable for human inhabitation.
Right.
It's when you start throwing in the deltas of what's happening outside predominantly that makes you need to pay attention to.
And I think what the point here is that when there's a big difference between the two is when water gets stuck as opposed to just flowing through as moisture, right? Is that it stops and precipitates. And if you know that you've got a big dew point problem, you're going to have more water to deal with than less. Is that part of it?
That's part of it. Oftentimes, and the interior conditions of the building have an awful lot to do with it. Ice rinks, indoor swimming pools, those are the obvious ones. But oftentimes people don't think about the fact that human beings,
Yeah.
we are portable heat units and moisture units. And if you've got a very high habitant ratio of people inside that building versus your space, every one of those people is a little furnace at 98.6 degrees Fahrenheit, and they're exhaling moisture and they're bringing moisture into the air. So, that's something that gets overlooked quite a bit, but it has a lot to do with what happens and how you need to control your vapor.
Makes sense.
So you've got your vapor retarder, and as I said, instead of referring to it as a vapor barrier, it's much easier in the building sciences to think of it as a vapor retarder. Your permeability of your vapor drive, there's class 1, class 2, and class 3 with examples listed on which is each of those classes. And based on where the building is built, code may require or not require different classes of vapor retarders. And then once you get into the geographic location of the building, then you have to pay attention to what's going on inside, because even though code may not require a vapor retarder, you need to be cognizant of the fact that you may need a vapor retarder so that your building operates properly.
And I think what's interesting is, you make the distinction between a barrier and a retarder is the fact that there are three classes. It's how much they're allowing through, right? And that's
That
depending on what you're going to need for the building and where it's built and so on, right?
that is correct. Oftentimes you'll hear class one, which is of the lowest permeance, referred to as a vapor barrier, and that's just a matter of semantics. But when you're talking about a class three vapor retarder,
Hmm.
it's kind of a misnomer to think of a class three vapor retarder as a quote vapor barrier because it is allowing vapor to pass, and it passes both ways. But because it's going to go from your low vapor pressure, from your high vapor pressure to your lower vapor pressure. So this map shows you your different climate zones and tells you when vapor retarders are required. Example, zones one, two, and three, it's not required. Zone four, class three or better is required. Zones five and six, as you get into the colder climates, it's class two or better.
It's
And that's
interesting.
where the consultants can help figure out not only what type of vapor retarder is going to work better, but where the vapor retarder is actually put in the wall. Sometimes it's better for the vapor retarder to be on the interior space. Sometimes it's better against the exterior space based on where it is and what it's doing.
And what's interesting about this map is how messy it is and how absolutely driven by counties it is, as opposed to, I mean, obviously the climate is driving it, but you can see some of these are very much, out of order. There's purple in the middle of the blue and so on. So all the more reason to be, cognizant of what your local AHJ requires.
So, so this is a cool photograph of how vapor retarder installation is important, but just as important here is the lack of an air barrier. This is an ice skating rink. That's in the Czech Republic where the guys are playing in an indoor rink in the fog because the air is bringing in moisture laden air. And when it comes into contact with the cold air coming up off the ice, the condensation's happening right where the players are playing.
Yeah.
And then this is actually an ice rink in the Atlanta area where they don't have fog. But when you walk in there, you can feel that it's moist. It
Yeah.
feels like a locker room. And the funny thing to keep away the fog, the owners had to install multiple of these dehumidifier units that run 24/7 so that it's not a fog bank inside. But most building owners, when they figure out if they want to the economics of building their building, they don't factor in the cost of additional equipment and the electricity to run that equipment constantly because there's no one paid attention to the air barrier or the vapor intrusion.
Yeah. I used to play hockey and it was always an issue.
Always. So the reason why air leakage and vapor diffusion are important, and air leakage is much more important than vapor diffusion, a sheet of sheetrock is going to allow vapor to pass through it through vapor diffusion. If you've got the same two sheets of board and there's no holes in the first board, you're going to get a third of a quart of water in a period of time. And in that exact same period of time, if there's as simple as a 1 inch hole in that, you're going to get 30 quarts of water moving through from the exterior to the interior of that building. So putting a vapor retarder on that sheet, but you still have the hole in the middle of it, letting the air in and out, is a huge problem. And it's something that gets overlooked quite a bit. And if you think about in building a building, how often there are light fixtures and cable TV runs and HVAC ducts that are punched through walls, and all they have to have is a little 1 inch hole, and you're going to get 30 quarts of water over a certain period of time.
When you think that maybe it isn't 1 inch in one place too. What if it's, a fifth of an inch in five places? When you start thinking like that, you're like, hang on a minute, it doesn't take a lot to add up to that inch or half an inch, whatever it is, but all of that's a lot of water to deal with, isn't it?
Yeah, and it doesn't even have to be the little hole or the things that you think of. Like I had mentioned, that a lot of air intrusion occurs at the edges and the details where one trade meets another.
Hmm.
And an exterior wall that meets a slab if at the base of that exterior wall in the slab, you don't have an air barrier between the two, then you may only have a 16th of an inch gap,
Hmm.
but it goes for 100 feet
Yeah,
or the length of that entire wall.
right.
And the amount of moisture from that air intrusion is just mind boggling. And that's, you know, in that situation, we found out that's the reason that the flooring was failing because the air was getting up underneath and the moisture that was coming in at the base of the wall at the foundation slab, the air that was getting in there was bringing in the moisture, and that's what was messing up the flooring,
Crazy.
causing issues.
And it just sits there. That's the point, right? Is maybe for a week or two, you're all right, but in 6 months, a year, 2 years, bad things happen.
Exactly.
We get cream of wheat again.
Yes.
So then we'll talk next about heat transfer.
Right. So the thermal barrier for the building is important to think about the fact that heat is going to transfer in three different ways. You've got conduction, convection, and radiation. Those are the three ways that heat moves. That's basic physics. If you took physics in high school, you can remember those certain things. The things that affect us, we think of thermal bridging, and that's something that has come more to light in these days. But thermal bridging occurs because the molecules are touching one another. So if you think back on when you were toasting marshmallows as a kid, you knew that that stick was going to get hot because you were holding it in the fire. And that's because the molecules of that metal rod that were holding the marshmallow are in contact with one another. The same happens on a building when the studs of the building don't have a thermal break between the interior and the outside, so the heat transfers. Or with roofs, when you have metal fasteners going down through a roofing system, coming into the interior space of the building and exposed to the exterior conditions at the top of the building, it's going to transfer the heat along the length of that screw, moving it in places that you probably don't want it to move.
And that strikes me as, again, one of those things that might be surprising when it's happening, right? Because you don't see, even more than moisture, you don't see heat flowing. So is this one of those areas you find that people will be surprised that when some trade has come in and done something that nobody had any idea that it really had an impact on the thermal performance?
Yes, it's interesting, and as you get more into the building sciences, you start driving around and looking at roofs where you can see the frost in the mornings coming off or the dew coming off, or if you're on a roof that's ever had snow or frost on it and you can see all the melt points from the plates of the
Yeah,
metal
yeah.
fasteners going down in there, that's thermal bridging personified. It's your absolute example there, but you don't think about, you know, when you're running a line down so that they could run a cable up to a direct TV satellite dish on top. That pole that's coming up through the roof system is transferring the heat and possibly air from the interior to the exterior so they can run their wires out to the satellite dish. So you've got the continuous insulation that the International Building or the International Energy Code is pushing for the entire world because we've become much more aware of the fact that when we waste heating and cooling, we're wasting energy, we're wasting our natural resources, sustainability. So, ways to fight thermal bridging is continuous insulation, thermally broken window frames, thermally broken insulated metal wall panels. The construction materials building industry is starting to pay so much more attention to preventing thermal bridging, and they're doing a good job of it. But we've still got a ways to go in making our buildings have a zero footprint. So convection is the second way that heat moves, and most people know the little thing that heat rises. They can think about millions of examples where they've been in an elevated position and it's hotter up there than it is down at the bottom.
Right.
And air moves through the building, through the walls, it moves between the floors. And if your air is moving in such a fashion that it goes outside the thermal barrier, but then can come back in, it can go up and bring more moisture in. In this one graphic that we're showing, the thermal barrier on this attic soffit is inboard of the actual soffit, but the air is moving up into the soffit, and it's coming up as hot air. It's getting cooled off in the wintertime, and it's coming back down into the other side. So the thermal barrier is very important to help prevent the convection and to move the movement of air, to prevent the movement of air or control it and regulate it in your walls in your structure.
You just described a heat pump, right? Like it's a natural heat pump where it's pulling heat out, cooling it off, and sending the air back.
Exactly. And then there's radiation. So the radiation is electromagnetic waves, and there's only three things that can happen to that big yellow ball of heat radiation that's in the sky every day. When it's coming into your building and it hits your windows, it's either going to bounce off of it as reflected light, it's going to be absorbed into the actual glass itself, heating the glass, or it's going to be transmitted into the building via solar heat gain. So it's very important to pay attention to not only what type of windows you use, but where they're located and what's being done to change the amount of solar heat gain where needed to pay attention to it. In other words, you've got low E coatings that can increase the amount of reflected light. But if it's a northern exposure that's not getting a lot of direct sun in the higher latitudes, then sometimes it can have less of a low E coating. So this is where working with a consultant and working with your actual window tradesman, those manufacturers have got a whole lot of information that can be helpful for your solar heat gain, the azimuth of the sun in periods of time during the year, and all of the different very complicated calculations that can help you understand and control your solar heat gain through the windows.
Love it. So our last thing is rainwater management.
So you've got your rainwater management, and as we talked about, all the different things, the 3Ds prevent the problems. But as I mentioned with the cancer, the bad thing is that if you've got the problems, you sometimes don't find out for a number of years. And you can run into health, safety, and welfare issues because the building could possibly collapse because that water in there has eaten actually into the structure. And there's a photograph here of an interior in a wall where they didn't realize they were having problems until all of a sudden things started falling off. And when we went into it and realized that water was getting in there and it was not being allowed to drain or dry, and it was just living inside the walls, and these were load bearing walls, the presence of the moisture was creating mold, which the interior inhabitants were then breathing, and it was eating at the columns and the structure itself. And so that things were falling off the building, and there was a chance of the actual building falling down. And then we ended up having to shore that structure up while the building enclosure problems got fixed.
And you can see how a lot of the concepts we've talked about until now kind of come together here. I think we'll end with vapor diffusion.
All right. So the vapor retarder, I talked about how based on where you're located, you're going to have the opportunity to use vapor retarders, but you have to be aware of the fact that you might not want something that's a vapor retarder in areas where you don't want it to be. This is a situation where a wallpaper contractor used a vinyl-based wallpaper on the interior of condos in Florida. So you've got a massive amount of moisture outside, the warm, humid air in Florida. The vapor drive is pushing that into the walls. And when it comes up against the back of the vinyl wallpaper acted as a class 1 vapor retarder, and they were getting condensation actually on the back side of the vinyl wallpaper, which grew mold. So the people inside were breathing mold because instead of the wallpaper being higher permeability, allowing that moisture to then dry out when it reached the dry conditioned space inside, it was being trapped against the inside of the wallpaper.
Awesome. Well, Tony, this has been an amazing romp through enclosure, and it's kind of the first of at least two we'd like to do. I think we're going to kind of skip ahead. I'd love to be revisiting some of this, and there's a whole bunch of other things that we haven't covered here. We've spoken now for almost 50 minutes. This has been awesome. Thank you for joining. And the purpose of this for folks that are tuning in for the first time is really to present the thoughts and the insights of experts like Tony, so that folks that are responsible for the building kind of have are able to review a lot of this and take a lot of this on board so that they're catching things before they become a big problem. So Tony, thanks again for being on the podcast.
Thank you very much. I really appreciate this.
So